In section 5 of chapter 13, evaluating a regression equation's ability to predict is discussed. And to evaluate a regression equation's ability to predict, we need to look at from the Excel output, which is the same output here that it was shown in the previous section. We have to look at two parameters. The R squared first. R squared is 0.7475. R squared is just equal to the correlation coefficient squared. Remember, the correlation coefficient is R. And we calculate it to be 0.864. I can do it right here again. Correl between B4 through B18 and C4 through C18. And it's 0.86463. Now, if we square this value, C20 squared, we get 0.7475, which is this value here. Right. What is this value? Well, first of all, notice that if we square a value that is between -1 and 1, we're going to obtain only values between 0 and 1, because negative values become positive values. So the R squared is a number that varies or changes between 0 and 1. Closer to 1 means very highly predicted values of y given the values of x. Values close to 0 means that we have very low prediction power. Well, in this case, we have 0.75, which can be interpreted as this. About 75% of the variation in y, the dependent variable, is explained by the variation in x, the independent variable. In this specific case, 75% approximately of the variation in copiers sold can be explained by the variation in the self-calls, which is a relatively high number. The other parameter or number that we can look at to evaluate the equation's ability to predict is what is called the standard error. Right here, 6.72. The standard error is called also the standard error of the estimate. And it is, as you see here, it says standard error. It is the standard deviation of the errors in the model. The lower the standard deviation is, the better the regression equation's ability to predict. This particular standard deviation is coming from the calculation of the square root of the variance that comes from the residuals. The value is right here. That is the previously called before and in previous sections of 13 and also chapter 12, MSE, mean squared errors. This is, remember, 58711. This is the sum of squares of errors. This is the sum of squares of the actual value of y's minus the predicted value of y on the regression line. I drew that before. Let me review that. If we have a value of y right here for a given x, and the regression equation goes through here, the difference between the actual value of y and the expected value of y, which is the y hat or predicted value on the regression line, that is yi minus y hat, the difference between the two. That is called the variation due to the error. But if we add all this variation for every value of y and square them, so we calculate the differences first and then square them and then add them up, we get the SSR. I'm sorry, the SSE. SSE, the sum of squares of the errors. And that is 587.11. When we take this value divided by 13, we obtain the variance of the residuals, 45.16, and it's called MSE. Well, the square root of that, it'll be the standard deviation of this number. The square root of this number is precisely 6.72, which is called the standard error of the estimate. And again, the lower this value is, the better the equation's ability, or the regression equation's ability to predict. And that is all for this section.